Hello everyone. Today I am going to discuss the two theorems that play important roles in public key cryptography, that are the Fermat's theorem and Euler's theorem. So in this presentation, the contents that I'm going to cover are the basic concepts of prime numbers, which include prime factorization, relatively prime numbers, and the greatest common divisor. Other than that, the main concept of Fermat's theorem and its proof, the Euler-Torsion function, the Euler's theorem, some applications of the theorems, and some examples. So prime number is divisible only by 1 itself. For example, 2, 3, 5, 7, 11, 13, 17, etc. 1 could also be considered prime, but it is not very useful in the case of these theorems. And prime factorization, to factor number n is to write as a product of other numbers. So that is, a whole number n can be written as a product of various integers such as a into b into c. For example, 100 can be factorized as 5 into 5 into 2 into 2. So prime factorization of a number basically is writing it as a product of prime numbers. For example, 143 is equal to 11 into 13. So what are relatively prime numbers? Two numbers are relatively prime if they have no common divisors other than 1. So 10 and 21 are relatively prime in respect to each other, as 10 has factors of 1, 2, 5 and 10, and whereas 21 has factors of 1, 3, 7 and 21. The greatest common divisor of two relatively prime numbers can be determined by comparing their prime factorizations and selecting the least powers. So here's an example of GCD. 125 can be represented as 5 cubed and 200 can be represented at 2 cubed into 5 square. So GCD of 125, 200 is equal to 2 to the power 0 into 5 square, which is 25. If the numbers are relatively prime, the GCD will be 1. So considering the following example, that is 10 and 21, thus GCD of 10 and 21 is 1. If that follows, then a prime number is also relatively prime to any other number other than 1 and itself. So coming to Fermat's theorem, Fermat's theorem states the following: if p is prime and a is a positive integer not divisible by p, then a to the power p minus 1 is identical to 1 of mod p, and also for every integer a to the power p is identical to a of mod p. This theorem is also known as Fermat's little theorem. It is widely used in public key, that's RSA cryptography and primality testing. Now coming to the proof of Fermat's theorem, we consider the set of positive integers less than p, this 1, 2 up till p minus 1, and multiply each element by a and modulo p to get the set x, which is a mod p comma 2a mod p up till p minus 1 a mod p. None of the elements of x is equal to 0 because p does not divide a. Furthermore, no two of the integers in x are equal. To see this, let us assume that ja is equal to ka of mod p, where 1 less than equal to j less than k less than equal to p minus 1. Because a is relatively prime to p, we can eliminate a from both sides of the equation, resulting in j equals k of mod p. Well, this last equality is impossible because j and k are both positive integers less than p. Therefore, we know that p minus 1 elements of x are all positive integers with no two elements equal. We can conclude that x consists of the integers 1, 2 up till p minus 1 in some order. Multiplying the numbers in both sets p and x and taking the result mod p yields the resulting equation. We can cancel the p minus 1 term because it is relatively prime to p. This yields the equation, that is a to the power p minus 1 identical to 1 of mod p, which completes the proof. Now we come to Euler-Tauschent function. So before presenting Euler's theorem, we need to introduce an important quantity number theory referred to as Euler's Tauschent function, written phi of n and defined as the number of positive integers less than n and relatively prime to n. By convention, phi of 1 is equal to 1. So phi of n, how many numbers there are between 1 and n minus 1 that are relatively prime to n? So if we consider n is equal to 4, then phi of 4 is equal to 2 since 1 and 3 are relatively prime to 4. Similarly, for n is equal to 5, phi of 5 is 4 since 1, 2, 3, 4 all are relatively prime to 5. Phi of 6 is equal to 2 since only 1 and 5 are relatively prime to 6. Phi of 7 is equal to 6 since 1, 2, 3, 4, 5, 6 all are relatively prime to 7. So from phi of 5 and phi of 7, phi of n will be n minus 1 whenever n is a prime number. This we can conclude. So this implies that phi of n will be easy to calculate when n has exactly two different prime factors, such as uh, 10 and 21. Taking that example, phi of p into q is equal to p minus 1 into q minus 1 if both p and q are prime. If GCD of a comma p is equal to 1 and a less than p, then we can conclude that phi identical to a to the power p 1 of mod p. So in other words, if a and p are relatively prime, with a being the smaller integer, then when we multiply a with itself by p times and divide the result by p, the remainder will be 1. So now coming to Euler's theorem. So Euler's theorem states that for every a and n that are relatively prime, a to the power 5 of n is identical to 1 of mod n. So if n is prime, because in that case phi of n is equal to n minus 1 and Fermat's theorem holds. However, it also holds for any integer n. So if we recall that f of n is the number of positive integers less than n that are relatively prime to n. So here we consider the set of such integers labeled as r is equal to x1, x2 up to x of phi of n. That is, each element x is a unique positive integer less than n with GCD of xi comma n is equal to 1. Now we multiply each element by a comma modulo n. S is equal to ax1 mod n comma ax2 mod n up to ax phi of n mod n. This set is a permutation of R by the following line of reasoning. Number 1, because A is relatively prime to n and xi is relatively prime to n, axi must also be relatively prime to n. Thus, all the members of S are integers that are less than n and that are relatively prime to n. There are no duplicates in S. If axi of mod n is equal to axj mod n, then xi is equal to xn. So, therefore, the following equations can be deduced, which are as given here. So, coming to the applications of the Fermat's and Euler's theorem, the main application is They play an important role in public key cryptography (RSA). Another major application is it is used in periodic decimal expansion. So here is an example. Here we chose two large prime numbers p and q. Let p is equal to 7 and q is equal to 70. Then we multiply p and q. Then we select the public key, that is the encryption key E, such that it is not a factor of p minus 1 into q minus 1. Now 7 minus 1 into 17 minus 1 is equal to 96. Factors of 96 are 2 and 3. So E has to be prime to 96. So let E be 5. Now we select the private key, that is the decryption key D, such that the following equation is true, which is D into E of mod of p minus 1 into q minus 1 is equal to 1. So here we substitute the values of E, P and Q in the equation. Let us choose D is equal to 77, since 5 into 77 of mod 96 is equal to 1, which satisfies the above condition. For encryption, we calculate the ciphertext CT from the plaintext PT as follows. CT is equal to PT to the power E mod of n. Now let us consider encoding of alphabets such as A is equal to 1, B is equal to 2, C is equal to 3, up till Z is equal to 26. We have to encrypt a single alphabet F is equal to 6 using this scheme, with B's public key as 77 known to A and B, and B's private key as 5 known only to B. So CT is equal to PT to the power E mod of 119, which is equal to 6 to the power 5 mod 119, which is equal to 41. So now we send CT as the ciphertext to the receiver, and also send 41 as the ciphertext to the receiver. Now coming to decryption part. For decryption at the receiver, we calculate the plain text PT from the ciphertext CT as follows. The equation used is PT is equal to CT to the power D mod n. So calculating, we get PT is equal to 2 to the power T mod of 119, which is equal to 41 to the power 77 mod 119, which is equal to 6, which was the original plain text, that is the code of. Thank you.